Hi, my name is Miranda Ross, and alongside my group members John Lacey and Emily Duplashan, we were given the task of evaluating the vapor liquid equilibrium of an ethanol water mixture and then using Raoult's law to compare our data to the compositions of an ideal mixture. If ethanol and water were an ideal mixture, it would follow Raoult's law as you can see in this graph. We know from literature that the boiling points of water and ethanol is 178 degrees Celsius respectively. Therefore, the saturation pressures were calculated in between this temperature range in order to find the mole fractions of each ethanol and water. All of this was done as if it were a perfectly ideal mixture. However, we know that an ethanol water mixture is not ideal. In real systems, it's extremely rare that the like interactions are identical to the unlike interactions. The vapor pressures can be treated as ideal because we were at a low enough pressure of 1 atm. However, we have to take into account the non-ideal liquid phase. When you take that into consideration, gamma has to be included into the equation in order to account for that non-ideality. Here we have a graph of our final data points that we collected to express the vapor-liquid equilibrium of ethanol and water. In this experiment, an Othmer still was used in order to distill the ethanol water mixtures into different compositions. The Othmer still sits on top of a hot plate that heats the liquid to the boiling point until equilibrium is reached. We monitored the temperature on the thermocouple, and once the vapor composition refluxed and the temperature remained constant for about 5 minutes, that temperature was recorded as the equilibrium temperature. Once this occurs and the vapor exits from the top through the condenser, samples were taken from the vapor portion as well as the leftover liquid portion. These samples were then placed into a gas chromatograph machine to measure the compositions. A gas chromatography machine is used to quantify the relative amount of different compounds in each sample. The sample is injected by a syringe into the oven where it's hot enough to boil it. The vaporized portion is carried by the carrier gas, which in this case was helium, through a capillary column. The column is a very narrow tube that has an interior surface coated with the stationary phase liquid. Different molecules in the sample will travel through the column at different speeds, or retention times. At the end of the column, there's a thermal conductivity detector. This senses changes in the thermal conductivity of the column output and compares it to the reference flow of the carrier gas helium. The GC then produces a series of peaks, one peak for each sample in the mixture. The area under the peak is a representation of the amount of compound in each mixture, and therefore the area was used to find the final mole fractions of our ethanol and water mixture after equilibrium was reached. So we compared those mole fractions calculated from the GC to the calibration curve that was made from known concentrations in order to ensure accuracy and precision. This graph is not linear because ethanol and water have different response factors. A response factor compensates for the irreproducibility of injections into the gas chromatography machine. So when calculating our final mole fractions using the calibration curve, we wanted to get rid of any variance that may occur when samples were rerun. After using a solver to find the most accurate ratio of response factors, we compared that data to the coefficient of determination to make sure it was the best we could possibly get. This provides a measure of how well the observed outcomes are predicted by the model, and with the coefficient of almost 1, we were pretty confident in the ratio that we came up with. So in order to make sure that we had the least amount of error possible, we calculated the root mean square error of the mole fractions, once the response factor was taken into consideration. As you can see, our final determination was a root mean square error of 0.049. And with that, we felt extremely confident in the calculations being used to find the final mole fractions we obtained from the GC data. This is the experimental data graphed in comparison to the ideal model, and as you can see, there's a pretty obvious positive deviation from ideality. Aside from that, there's also an azeotrope that occurs in this ethanol water mixture. Although it's not perfectly visible in this graph, we know from literature that the azeotrope, or the minimum boiling point in this scenario, would occur at 95.6% ethanol. This graph is the known data of ethanol and water. As you can see, it better shows the azeotropic point that occurs in this particular mixture. Overall, the graph matches up extremely well to our data that was collected after we ran the experiment. So we know that there's a positive deviation from ideality. Now we want to confirm it and quantify it. So, by rearranging Raoult's law and using the known information as well as the previous determined mole fractions, we discovered that the gamma for all of our different data points was above 1. Gamma being greater than 1 confirms the positive deviation from ideality in phase equilibrium. Molecularly, unlike interactions in liquid aren't as strong as like interactions. Therefore, the two species, when mixed together, are not held together as vigorously in the liquid phase, which means more molecules escape to the vapor phase in comparison to an ideal solution. So, when comparing our experimental data to the theoretical data of an ideal mixture, we can confirm the positive deviation from ideality and calculate the gamma to quantitatively express that deviation. So, with that being said, thank you for listening and I appreciate your time.